Okay, good afternoon, everyone. I think we can start. It's 3 o'clock. So yeah, good afternoon. Welcome to the panel lecture. And I'm doing this on behalf of Stefan, the chair of our department. We need to deal with something unplanned. So yeah, following the tradition, I want to briefly talk about the background of the panel lecture. So then I will like to have Michael, the host of the panel lecture, to introduce our speaker. So Professor Stanford Saul Penner was the founding chair of the Department of Aerospace and Mechanical Engineering Sciences, AIMS, at the University of California, San Diego in 1964. He also served as the director of the Institute for Pure and Applied Physical Sciences from 1968 to 1971, and the vice chancellor for academic affairs from 1968 to 1969, and the founding director of the UCSD Center for Energy Research from 1974 to 1988. He was the founding editor of both the Journal of Quantitative Spectroscopy and Radiative Transfer and Energy. He served as an advisor to the U.S. President's Office of Science and Technology Policy and the U.S. Department of Energy. Professor Saul Penner is the author of more than 300 journal articles and 7 books. He has received numerous professional honors, including the election to the NAE, the American Academy of Arts and Sciences, and the International Academy of Astronautics. He has also been awarded Distinguished Associate Award from the U.S. Department of Energy and the Founders Award from National Academy of Engineering. So in 1999, the Department of Mechanical and Aerospace Engineering established the Saul Penner Stanford S. and Beverly P. Penner Distinguished Lecture Series. And in the past, Professor Saul Penner attended some of these lectures, but unfortunately in 2016, he passed away. So now I would like to invite Professor Michael Fraser to introduce our speaker today.
Oh. All right. Yeah, so today we are honored to welcome Professor Zhigang Suo as our fall Penner lecturer, and it's my pleasure to provide this brief introduction. Professor Suo is the Alan E. and Marilyn M. Puckett Professor of Mechanics and Materials at Harvard University, where his research focuses on the mechanical behavior of materials and structures, including ceramic and brittle materials, but more recently, soft materials, especially in regard to their durability, which I'm sure we'll hear more about today, given the title. So Professor Suo is author of over 500 publications with nearly 100,000 citations, and the impact of his work extends from soft robotics to electronics to medicine. And in just looking over his website, at least paper number 351 in particular is one that has inspired my own research. So I'm pretty interested in that. So for this work, he has received the recognition of several esteemed bodies, including the German Humboldt Foundation Research Award, the Prager Medal of the Society of Engineering Science, and the Pi Tau Sigma Gold Medal from the American Society of Mechanical Engineers. Professor Suo is a member of the National Academy of Engineering, the National Academy of Sciences, and just last year elected to the American Academy of Arts and Sciences. And just to bring this introduction to a close, one last thing I have to mention, of course, is that beyond his research accomplishments, Professor Suo is active in promoting the mechanics community. As the co-founder of iMechanica, the world's largest online platform for mechanics and mechanicians, with tens of thousands of registered users from around the globe. And so without further ado, I give the floor to Professor Suo, who will give a lecture entitled Tanglemer, a polymer network in which entanglements greatly outnumber crosslinks.
Thank you, Michael. Thank you. Thank you, Shengqiang. Thank you for this invitation to give this lecture. Also, thank you all for coming. So, the lecture today has this title, Tanglemer. Tanglemer is a new word we call this kind of material. This kind of material, so we have a definition, a polymer network in which entanglements greatly outnumber crosslinks. So here's a picture of a tanglemer, schematic. So here's a polymer network. You have a polymer chain. So this polymer chain and this polymer chain is a crosslink. The crosslink is a covalent bond. So you can also see this red polymer chain, decorated red, is entangled with the other polymer chain. So that's entanglement. So we are especially interested in the material such that the number of entanglements here is 1, 2, 3, 4, if you count, are greatly outnumber of number of crosslinks. Here we just illustrate 2. How many? How much more? How many more? So I'll show experimental evidence. We have between 2 crosslinks, we have over 100 entanglements. So that's what's a tanglemer. What I'm going to talk to you about is why tanglemer is so important to us in terms of mechanical performance. And I also try to describe to you how we prepare tanglemer experimentally. So that's a game. All right. So some background. Some years ago, when Shengqiang was still a baby, the group, other group members published a paper, which turns out to be a very popular paper. We published in 2012. Shengqiang, was this year you left the group?
Exactly. Missed the paper.
Missed the paper. Anyway, so this paper, we demonstrate a class of hydrogel. I'll show a little bit detail next slide. Alginate polyacrylamide hydrogel. Hydrogel is just a polymer network with a lot of water, 90% water, 80% water. So this particular hydrogel became famous because we show it has, we make this material and we show it has enormous toughness. Now in mechanical engineering, everybody is a mechanical engineer. We know what is toughness. Toughness is a resistance to crack growth. So in particular in this material, here this material is transparent. So you see the black background. This material can be stretched 21 times. It's a very stretchable material, more stretchable than rubber. So, and this material, if we make a cut, there's a crack. This is how we measure the resistance to crack growth. We cut a crack and then pull this to watch whether the crack will grow or not. In this case, crack does not grow. What you are looking at is just the material just deform. The crack doesn't grow. So up to a stretch of 17 times. So in mechanical engineering or mechanics material, we have a way to evaluate toughness. This material have a toughness about 10,000 joules per meter squared. So I already mentioned it can be stretched 21 times and contain 90% water. Now, so for this number, many of you may not appreciate this gigantic number. So just compare with a number you are familiar with. Tofu, jello, about 10 joules per meter squared. 10 joules per meter squared is a pretty tough tofu. If you your tender tofu, your tender tofu, the value is even lower. So most gels people prepare in the lab is about 10 joules per meter squared. So we're talking about several orders magnitude difference. Contact lenses cannot be tofu. It has to be reasonably tough in eyes. That's 10 joules per meter squared. Our cartilage is 1,000 joules per meter squared. Natural rubber itself is comparable to this material. So so it's a very tough. We're very proud of this material. The field also rewarded us with 5,000 citations, more than 5,000 citations by now. So it's a good paper. Now, we were very embarrassed by this paper as well. So there is no flaw, no fraud, anything. It's just some property is not actually very good. We later find out. So first about the goodness of this paper. So this paper is made of, as we said, it's a polyacrylamide. Polyacrylamide itself is a hydrogel with a polymer network with a lot of water in between. So, and the toughness is 1,000 joule per meter squared. This is the material. And then there's alginate. Alginate is a tofu-like material coming from the seaweed. It's a biomaterial. So this alginate has a long chain. Between the chain, the crosslink is not a covalent bond. It's a calcium ionic crosslink. So the material is also brittle because this crack will unzip calcium crosslink and propagate forward. So in propagating forward, these other calcium crosslink remain intact, doesn't contribute to the energy dissipation. So the version of material we made is a combination of two at this molecular scale. So we have, so you have this polyacrylamide, this guy, and we also interpenetrating with this alginate. So before you break this chain, this polyacrylamide chain, so here's the polyacrylamide chain, the stress, because you have to break, this is covalent bond, the stress is high enough that can unzip large volume of ionic crosslink. Therefore, you dissipate a lot of energy. So the large volume, this scale is on the order of millimeter. It's much larger than atomic dimension. So this gives us this high number. So toughness is really very high, really very high. We call it black magic. It's a dark magic. Brittle plus brittle equal to tough. Okay. So we were very happy about this. People cite this paper a lot. However, some years ago, so when you have too many students, the later students will attack former students to find problems of former students' work. They did another test, too many tests. They say in mechanical engineering, we also have another test. It's called a fatigue test. We do cyclic loading. So again, this is a number, joule per meter squared. This is called energy release rate. So as I mentioned, the toughness itself is 1,000 joule per meter squared. We actually literally later version, we have more than 1,000 joule, 10,000 joule per meter squared demonstrated for the same material. Now, but if you do cyclic loading, this G is now the amplitude of the cyclic loading. So even at, let's say, pick up a number, let's pick up this 160 number, even at this low value, you still get a crack growth. This C is a crack length. The vertical axis is growth per cycle. You get about a few micron per cycle growth of this crack. Now, this material is not very useful. 2 micron per cycle, after 1,000 cycle, you have millimeter cracks, right? So this is called a fatigue crack or crack growth under cyclic loading. Now, so then you say, okay, you reduce load. You reduce about a 50 joule per meter squared. We cannot detect crack growth anymore. So this number is called a threshold, fatigue threshold. Fatigue threshold is a 50. Toughness is a 10,000. So huge difference between this. Of course, everyday life we have the experience. If you cannot break something one time, you break it many times, maybe not 10,000 times. So fatigue crack growth is very important. So we were very embarrassed by this material. So of course, after this student graduates, there's a future student to say, we are going to correct this problem. So I'm going to talk about the correction of this problem. All right. Oh, incidentally, I will show later that 50 should not be, we should not be embarrassed. This is 50 joule per meter square for fatigue threshold is a very common value for all polymer networks, including the golden standard, which is natural rubber, 50. We were just naive at that point. So it's a fundamental limit, regarded as a fundamental limit, not well understood at that time. Now we understand better. Now I'm going to show you we can enhance this value to 1,000. That's a recent achievement, recent few years. Really proud of this. Anyway, so of course we will have a future student, they will attack this work as well. So no doubt. So the life goes on, right? Okay. Now, so this also brings us to understand mechanical engineers, polymer engineering was not really my original field. I have to learn some basics. So here's one student who taught me a lot. He was a chemical engineer by training. Recently, we'll have a paper published in review articles, more than 100 pages review articles about the fracture and fatigue in polymer network. So anyway, so some basic terminology. I know many people are not really clear about the basics for polymers. So here's basics. So as I said, they have this. So we have long chains. So this red chain, so it's just we decorate with a false color. And here's another chain. Now we differentiate this idea. So this chain is really long chain, but between the chain you have a crosslink. Here's one crosslink along this chain. Here's another crosslink. So if you look at this blue guy, here's one crosslink, another crosslink. Between two crosslink, we call it a strand. So a chain is divided into many strands by crosslinks. So, okay, so we also said that along a chain, so if you look at along a chain, this is a repeat unit, This between repeat unit, that is a covalent crosslink. Shenqiang told me that somehow he qualified himself to teach polymer science. It's unbelievable. I'm really proud of him. He did not get a qualification from Harvard. I know that. So he qualified himself. Anyway, so we have a covalent covalent bonds link the monomers or repeat unit into chain, and we also have a covalent bond cross-link different chains. So these are covalent bonds. Now, in polymers, we also know there are non-covalent bonds in between the chains, right? So that non-covalent bonds, that was what we showed about this ionic crosslink in alginate. That give us a huge toughness, right? So that's also important. Okay, yeah. So then we say, okay, what is about crack growth? Crack growth is not, so if you study polymer science, polymer physics, polymer chemistry, crack growth doesn't really figure heavily in these textbooks yet. They should be, but they're not. So it is people like us talk about polymer, the crack growth. We hope next generation, maybe Shenqiang write his book, fracture will be included in the polymer chemistry, polymer physics. Anyway, so now, so here's a crack growing in a polymer. So we are going to focus on very important class of crack growth in that it's a localized irreversible process in the sense that the majority of material is still elastic. So the reason being, in most applications, you want material more or less elastic. You want to use it repeatedly. Come back, reload, come back. You don't want to have a plastic deformation, it's complicated. So the materials are mostly elastic. However, if you have a crack growth, of course, at the crack tip, you have active irreversible process in the sense you are going to break chains. That's irreversible. break chains. Also, you have this non-covalent interaction between chains cause friction, cause viscoelasticity. You don't break chains here, but there's a large region you have a viscoelastic deformation, which is dissipative. It's irreversible. So this scale, this red scale, this dissipation zone is still small compared to this elastic body. Now, what is also interesting is that you have scars. So once the crack pass, get into the material, you have the material left behind. So the material is now not in any process anymore. It's in equilibrium now. In equilibrium, but this equilibrium, you have scar tissue, right? You have the broken chains and some misalignment inside the material. So that is a generic process of crack growth. So quite intricate at a molecular level. You have all these things. Now, so then we ask a fundamental question. What is so different between a glass, window glass? This room is spectacular. There's no window. So normal room has windows. You don't see them, it's transparent, but there is window. Anyway, so glass is brittle. We all know that. It shatters. Rubber doesn't shatter. What's the difference in the molecular level? Let's talk about it. So there is a classical work, probably 100 years ago, studied this kind of thing, Griffith's paper. So now, if you have this is a glass is essentially atomic solid. So between individual atoms, you have covalent bonds, right? So when you have a crack coming to this covalent bond, you break this covalent bond, then you break the next covalent bond. All these other covalent bonds remain intact. So in this sense, stress is highly concentrated. It concentrates to individual atomic bond. Of course, you say, oh, maybe this guy has a stress concentration. Yes, but this stress, you can count number of bonds, right? Here's a single bond, but there are several bonds surrounding this. There are even more bonds surrounding that. So the stress at a bond decays rapidly over distance at atomic scale. Now, rubber is different. Rubber has long chains, we just said, right? There are maybe 1,000 monomers, repeat units along a single strand. Now, when this crack coming to this strand, right, it try to break a single atomic bond. You only need to break one atomic bond for this to move ahead. But before this break, the entire strand is under high tension. Why? Because between two strands, the interaction is non-covalent, it's very weak. So that high tension is able to transmit over long distance along the entire strand, right? So when you break a single, let's say break this guy, break a single atomic bond, covalent bond, the entire strand energy is dissipated. That's why it's so much tougher. Just any rubber is tougher than glass, right? So many years ago, this famous model, Lake Thomas model, find a scaling. So the threshold, the fatigue threshold under cyclic loading, scales with the square root of n. N is the number of repeat units along the strand. So, all right. So at this point, we're naive material designer. So I know how to enhance the threshold. All I need to do is make the strand as long as possible. Then I increase n, I increase threshold. So, boy, we're clever. Why not people didn't see that? Why not don't see that? Okay, so then we have a lot of students, right? Students write paper to say why people didn't do that. So it turns out there's a conflict. There's a conflict between this threshold and the modulus. The modulus is just elastic modulus to resist deformation. you can have a pretty good intuition. If your strand is very long, then this network is very floppy. The stiffness will be very low. So here we plot some experimental data from the literature. Here's the horizontal axis, stiffness, modulus. Modulus is scale with a number of repeat unit, 1/n. The longer n, the lower E. And the threshold we just said, scale with a positive square root n. Longer n, larger G threshold. So the data is negatively correlated. So this is a threshold, that's a stiffness. So if you want to have a high threshold, you're going to have a lower modulus. So many applications require some stiffness. All right, so if you're dealing with hydrogel, this whole thing is even worse because a lot of things are water, doesn't even carry load. 90% volume is water in the hydrogel. So this doesn't really work. This meaning just increasing N is not a solution. So you have more students. Literally, the student, this is Kim, he came here to give a talk, Zhigang Suo Kim. He was obsessed with this conflict. He was a Korean. He was skilled in resolving conflict. Yeah, our president should hire him to resolve conflict. So here's a clever idea. He literally, this is his idea. He explained to me. So I was telling Shenqiang, to my credit, I understood him for the first time. Immediately, I understood him. So yeah. Anyway, so here's the idea. If you have a lot of entanglements, you can see that the modulus, the entanglement also give you modulus, right? So the entanglement, there's a number of monomers between two entanglements actually set the modulus. The number of entanglements set modulus. So now, so this is just if you don't break any chain, all the entanglements resist deformation. They're good guys. Now, however, when you just break single atomic bond, you notice before you break any bond, because this is just entanglement between two entanglement, their interaction is non-covalent. It's very weak in the rubber. It's a liquid-like interaction between the non-covalent bonds. So the high tension can be transmitted over the entire strand, right? If you break single atomic bond, the entire strand energy is dissipated. The longer the strand, the better. So you scale with N. So the moral of the story is to resolve conflict. You do not punish anybody. You give resources to both. You give a different resource. The threshold required number of monomers along the strand, you give them longer N. Okay. The modulus depend on to make a strand short. You make a strand short. That's all you need to do. So that's why we need to have entanglements greatly outnumber crosslinks. Then you resolve conflict. That was his idea. So how do we do that? The guy was a mechanical engineer by training. He learned, so there's some, so this guy is a chemical engineer. So he learned things from chemical engineers in the group. Very good. So this is a polyacrylamide. I have to learn from these guys. So polyacrylamide has a lot of water in it. Water is a solvent, water molecule. You also have a monomer. Monomer is a acrylamide, has this double bond that can make a link. So cross-link has two double bonds that can link to both. And then this is the initiator. Initiator try to start the reaction. So there, here I will, so I'm going to mention W. W is a water to monomer number ratio. How many water molecule relative to acrylamide? We're going to talk about this number. Anyway, so this material is a relatively easy to prepare. It's quite a standard material for people prepare hydrogel. Worldwide, many labs do that. We choose that because it's quite simple. Only 4 ingredients you can prepare. Now, so, okay, there's a Zhigang Suo Kim has this idea. He wants to prepare Tanglemer. All right. So now regular hydrogel, our group, even in our group, have been preparing this hydrogel for more than a decade by his time. So regular hydrogel, remember, hydrogel has 90% water in it, right? So what people, regular hydrogel, regular people do hydrogel this way. You have a lot of water in the precursor, in this solution. How much water? For every monomer, typical value is you have a 20 water molecules. That works about 80, 90% water. All right, volume percent. If you do that, so the chains will be far apart. So in this case, if chains are far apart, they don't have a lot of entanglements. Nobody talked about this fact before. And he came because he wished for more entanglements. He said, here's my opportunity. All I need to do is the following. Oh, there's a last step. Because after you make hydrogel, right? The hydrogel is typically used in body, in contact with water. That hydrogel need to be stable in water. So the way you make it stable, just put in pure water, let water swell this hydrogel, you form a stable network. That's end product. So that's why hydrogel has a lot of water in it, 90% typical. All right. So Zhigang Suo came along to say, this is what you do. You don't put a lot of water in the beginning. You make monomer crowded. How crowded? The best he can do is every monomer, he only put 2 water molecules. That's a lot less than this guy. This is 20, right? So because the polymers are so crowded, they have opportunity to entangle. Entanglement, yeah, he doesn't have a little hand to stitch them together. It's all thermal motion, right? So if they're crowded, they entangle. Okay. So, and then he still need to do last step to make a stable hydrogel by put this thing after crosslink, you swell it. Now, notice, after crosslink, then when you swell it, entanglement cannot be disentangled because you already crosslinked it. The entanglement is locked in. So that's how he prepared Tanglemer. So now some result. So for regular hydrogel, so you can see this is logarithmic. Modulus is orders of magnitude lower. Orders of magnitude lower. Regardless of your however many crosslink you put in, this is the issue. Orders of magnitude lower. Now for Tanglemer, highly entangled hydrogel prepared by this way, both hydrogel is stable in water. This measurement is done after sweating. So you can see the stiffness is very small, very small if your crosslink fraction is really low. This crosslink fraction really is a number of crosslinker divided by number of monomer. It's pretty much how many monomer in between to the crosslink. If you put too few crosslink, the network is not well prepared. The chains are not really linked together. So your modulus is very low. After some value, maybe around 10 to minus 5, 10 to minus 5 means for every one crosslinker, we have a 10,000, 100,000 monomers. So very few crosslinkers, very few. You already reach the modulus. Furthermore, when you increase the crosslinker in this range by change by about 2 orders of magnitude, you do not increase modulus. That's where we know that your entanglement is about 100 per crosslink, right? Because when you have lots of entanglement, the modulus is dominated by entanglement. Adding crosslinks don't change modulus. You only change modulus when the number of crosslink overtake the entanglements. So that's our evidence, about 100 entanglements per crosslinks. Okay, so we're very proud of this. And then this is just a photo to show that for this highly entangled hydrogel, it really, yeah, stand up. For this regular hydrogel, it's so floppy, it's horrible. So that's what happens. This was made by previous student. This is right. Science progress. Right. All right. So now this hydrogel for polymer, people always has the impression that the polymer is highly hysteresis because you have a chains rub against each other. For hydrogel, this particular hydrogel, because the chain and the chain in between, you have water. Water has extremely low viscosity. So, and we ask the question, if you have an entanglement, does the entanglement cause you problem, give you hysteresis? So we did this test. We say, okay, I do stress strain curve. Stress going up, and this is a stretch, how much you elongate. You can load up and load down. You see the hysteresis is negligible. So entanglement doesn't really increase hysteresis very much, negligible. Okay, very good. So right, so yeah, hysteresis is good. Furthermore, you can change the loading rate, this strain rate, right? By this is 2 orders of magnitude. You can see the stress strain curve is really insensitive. Really insensitive. Very good material, very lasting material. Very proud of it. All right. So now this is probably for most mechanical engineers, love it. So this is a stress and a stretch. So however you prepare your regular hydrogel, you can make it stiff by putting a lot of crosslink, or very soft, very few crosslink. Your stress strain curve is just way below, by orders of magnitude, below the highly entangled hydrogel. All right, so this material really is good by ordinary measurement. All right, so bear in mind, Zhigang Suo didn't even change chemistry. It's just a change the step during the preparation, right? So it's a generic. So you can modify or to re-examine all polymers existing. So that's why it's a fundamental in that sense. All right, so I'll show other polymers shortly. Now fatigue threshold. So this is a regular hydrogel. This is done by old student, right? Things to tear down, old student. So it depends on the water fraction. So we have some range for the ordinary water fraction, 90, 80%. You have the fatigue threshold below 10 joule per meter squared, very low. But for Tanglemer, we reach to 200, right? By at least order of magnitude difference. No problem. No problem, easily. So he was very happy about that. So then we say this idea is so powerful. It's independent of chemistry. All polymers can be modified. So what is a highly valuable polymer we can verify? If you're a bioengineer, you will recognize this PEG. PEG hydrogel is a worldwide leading polymer hydrogel used for tissue engineering. So the feature of this is in most lab, academic lab, or actually in many applications, people don't start with monomer because the synthesized polymer itself, synthesize from monomer to polymer itself is too difficult for individual lab. So what people do is you buy polymer chains as a powder, and then you swell it and you cross-link it. That's standard procedure for application. So you don't start with monomer. So Zhigang Suo's idea of you start with monomer, make it very crowded, that idea doesn't work. Doesn't work. So we need to think about how, if you're given polymer, for whatever reason, later on we'll show natural rubber, nature gives you natural rubber. You don't get natural rubber and chop it up into monomer and then make a polymer again. You don't do that. You need to use existing polymer chains to make Tanglemer. How do you do that? That's a question. Okay, so this is a traditional making. So traditional making, people already know this, that because you with an existing polymer, and you do this crosslink, you need to be stable in water, swell with water. Then your chain cannot be very long. If your chain is very long, you can swell a lot of water. Then the material is just too floppy, you cannot use it. So as a result, people already know when you buy polymer, please buy polymers with short chains, and then do this. As a result, I'll show you the number. The material is extremely brittle. It's brittle, very limited. There's really severe limitation of this material, even though this is the most popular, among the most popular hydrogel used in bioengineering. All groups know how to do this, and all groups essentially do the same way. So then we have this idea. So this is a newer student. So learn from Kim. He said, also, here's the idea. Right? We're all Asians. We know, right? We do kneading. We do kneading. So you have a powder like a flour, right? You can put a little bit of water in, not too much water. Don't make it tofu immediately. Look like a dough. Make a dough. Make a dough. So make a dough, as you know, if you just put a little bit of water, you need to mix. The way you mix is by kneading, literally kneading. Then the water and the powder will be well mixed. This is a knead and anneal. So anneal step is allow the chains to entangle together. Again, the reason you want to have very little water is because you want polymers to be very crowded, able to entangle by this thermal motion, right? So after that, then you do crosslink. You do crosslink, and then you put into pure water to swell into equilibrium. That way, you will prepare a long chain and lots of entanglements. You prepare high Tanglemer PEG, PEG. So this is just a photo. So like a dough, right? In the beginning of a kneading, you have your particles still there, but after just 7 times kneading, it's already mixed very well. It's a highly hydrophilic material. Yeah. So kneading is not too hard. Kneading need to be gentle. Gentle. Now we know why you need to be gentle. You don't want to break chains. Don't break chains. All right, good. And now you can see the difference. So this is a regular hydrogel. The strength is very low. It's very stiff because the crosslink is very dense. So this highly entangled PEG hydrogel, you can see the strength is much higher, very stretchable. It's a totally different class of material now. You open up applications. So yeah, I've already talked about this difference. I showed you individual just by comparison now. So traditional material, short chain, no entanglement. Entanglement was not in people's thought in making this gel. We prepare very long chains as long as we can buy. And then with a very sparse crosslinks with lots of entanglements. That material give you high toughness. Now the number, there are lots of number we compare. So so in our comparison, we make a blue material wing, red material loose. So this is a traditional material. Traditional material. So the fatigue threshold is, as I said, very low, 8 joule per meter squared, and this Tanglemer, 100 joule per meter square, right? It's a real when you do this. All right, so then we get more ambitious. What is the most impact we can make with this idea? So we decided the idea that it must be tire. You need a rubber hydrogel, right? This is rubber. This is not a hydrogel. Water is irrelevant. Rubber, you have polymer network. So around that time, so this is a 2021, it was in the news. There was a paper, Publishing Science, to resolve a long-standing mystery. The mystery is the following. For many decades, that people knew, especially in state Washington, that, after rainstorm, salmon died in river. There's a correlation between rainstorm and death of salmon in river. For many decades, people speculated what was the reason. Maybe rain hit salmon, or what happened? How did that work? All right, how did that work? And this group is a chemistry group, made a hypothesis. He said, on the road, there are tires. Tires shed particles on the road. During the rainstorm, these particles get into the river stream. And there must be something poisonous to the fish. And the fish eat these things, leached out from rubber particle, and fish die. So this is a hypothesis that can be tested, right? All you need to do is feed whatever you can find in the rubber and feed to fish, which causes death. And they found this. This is a paper made into Science. They found that it is a compound used for antioxidant. It's known rubber is vulnerable to oxidation cracking. So this problem was identified, but to this day, the problem was not resolved because the antioxidant is necessary in car. So we said, this is an opportunity for us. Maybe we cannot find this antioxidant, but at least we can enhance mechanical property of a tire so that it doesn't shed as many particles. Maybe some fish will be saved by us. We didn't quite do that, but I'll show you what we did. So our initial idea was the following. So conventional wisdom, the particle, the tire is a composite of a polymer and hard particles, typically carbon particles. So the conventional wisdom is the following. The particles greatly amplify stiffness, make it stiff. That's true. But not fatigue threshold. People had decades of data to show fatigue threshold stay at about 50, maybe 200 joule per meter squared, not higher. So that conventional wisdom. So we said, oh, maybe they didn't know the secret of Tanglemer. Maybe if we make it into long chains, we can amplify threshold. That's a hypothesis. So we further become very ambitious. We say, after we make long chains, become fatigue resistant, maybe the carbon, this tire will not shed too many particles on the road. And maybe fish was saved. It's a better days, right? We have other things to worry about. Not about, I overheard, and that's a funding, we didn't worry about that. We worried about a fish in those days. So that's a hypothesis. At that time, the group didn't know how to really work with a long chain natural rubber, which we start with something we know about. So here's a, so we essentially synthesize the material with monomers. Because with monomer, we easily know how to make it. It's a rubber reinforced by particles. It's a silica particle. So we work with this guy. He's a retired CTO of a local company, Cabot, who the company specialized making particles for car tires. So he had his old buddy in the company supply us with the particles. So we synthesize these materials at Harvard. So here's the idea, the conclusion we find out. So so we have these chains. So here's one particle, here's another particle. In between particle, you have rubber. So this rubber, we made this rubber have enormous long chain, not natural rubber, synthetic rubber in our case. So as we already know, when crack coming along, so the high tension crack cause high tension here, is transmitted to the entire strand. If your strand is long, you dissipate a lot of energy. That was our initial thought. But then the student, this is a stick, he keep getting data even much higher than our expectation. This is the data. He was the first person discovered in the lab that we can achieve the threshold 2000. So we said, oh, the Jason, you're not as good as Kim. So work with Kim. You must be doing something wrong with the experiment. Kim only achieved, some 100. You achieved 1,000, and you must did something wrong. So the two went back, come back, Zhigang, we have an issue. Our threshold is higher than anticipated. So we couldn't publish paper now. We have a number we cannot understand. So eventually we cook up a new story. A new story, why toughness is even higher than contributed by long chain. We said it's the following. So here is a hard particle, in our case, a silica particle, glass particle, nanoscale particle. So we said in between two particles, there is a layer of rubber. So another particle layer rubber. It's well known in the rubber industry. If your particle is beyond a certain percentage, the particles will cluster. In the sense, on average, some particles, a group particle will be closer than other particles. In between particles, you still have a layer of rubber, but that layer becomes very thin, very thin. All right, so then our story is the following. So before this layer of rubber break, because this is silica is a rigid material, the same high stress will be also here. So when you break one neck, you release energy of many necks. So all you need to do is 5 more necks, then you go to 1,000, right? Previously, we already achieved several hundred, 200. 5 necks, you're done. So that's so we call it so we're academics. We call it multi-scale stress deconcentration. 2 scales, chain scale and particle scales. All right, so that works. So as I said, this guy get a threshold, G threshold, to 1,000, and still maintains a similar modulus. Same modulus. So this paper, yeah, made to Nature. The editor is incredibly good. We motivated this paper by fish. So the editor is very sharp. Show me the fish. If you since you haven't shown your tires running on the road and reduce the number of particles on the road, you cannot talk about a fish. You can talk about your fatigue resistance. I'll let you publish your fatigue resistance. Very kind editor. So we follow. So fish get out of the story. There's no story. No fish in the story. Anyway, so we move on. So but our ambition stayed. We want to make impact about natural rubber. So natural rubber, you all know natural rubber come from the tree, all right? So you need to dry and you mix shape crosslink. So in order to make this happen, you have a very long chain. So in traditional processing, you just use this roll mill or blender, you cut chains short, and then you crosslink it. So that's a conventional making. Every car company is making this way. What we hope is, so wait a minute, maybe you can make a long chain and don't break it, and you gently knead it, and maybe this will give you better property. So what I'm going to show you is this way we did. We actually enhance, the natural rubber toughness by orders magnitude, right? So this is all the conventional rubber, all kinds of rubber, natural rubber and synthetic rubber. Here's our natural rubber Tanglemer. So toughness, fatigue threshold enhanced by orders magnitude, and even toughness enhanced by 1 order magnitude. So the Tanglemer really worked. Yeah. So then we also come along to say, can you also do this with a particle in it? It's even more challenge, right? You need to blend particle, silica particle, carbon particle with long chains. No, we actually make it. The paper was actually already submitted and rejected. We submitted again. So we will try and keep trying, keep trying. But the data doesn't lie, right? Toughness, there's no question about data. Toughness goes up, fatigue threshold goes up. So, and we also, so I need to wrap up soon. But once you work with particles, so remember, this is Yakov coming from industry. There's a tremendous industry know-how about particles and rubber. So not scientific study, but just a trial and error know-how. In particular, there's an important know-how is the particles actually form this percolating network. That's very important for both stiffness and toughness. Not fully understood for toughness, we investigate that, especially in Tanglemer, where the Tanglemer will help you even better. So that's one story. The other story, I didn't know about this before at all. It's in the car tires. The particles are not really spherical particles. They are actually aggregate. So there are some primary particles. The particle, they actually covalently bonded. So into an aggregate, each aggregate maybe 10, 20 individual particles. So because these are particle aggregate, it's very hollow. The rubber actually get into the aggregate. So it's rubber and aggregate are intertwined. You can appreciate how important it is for mechanical behavior, right? It's not just bonded, they're intertwined. So we're investigating that. So the paper submitted. So we are also doing something. So we try to make impact. We have one good idea. One hammer. Is this right? No. We have one hammer and looking for all kinds of nails, a long one, short one, flat one. So we also look at this carton for milk, for juice. So people know that industry know that it's a problem. So all the paper product is coated with a layer of polymer. That layer of polymer is a polyethylene. It doesn't degrade in nature. It takes 100 centuries to degrade. So you think you are using paper, but you also use polymer. So we say, can we also take care of that problem? Again, we haven't taken care of that problem, but we did learn how to make this coating and make this coating with a biodegradable material. That we can do. So we're still, we publish some papers, make it work. So I won't talk to you about detail as paper is published. Again, we learn how to make this material both biodegradable and very tough and thin coating. It's doable. So the property has a good threshold, fatigue threshold, a good toughness, etc. So I will skip this part. Let me summarize. The basic message is really this cartoon. So Sensipia, I hope you are not disappointed. I only showed one equation, and that equation was derived by somebody else in 60 years. So Sensipia, I used to be a theoretician. She expects me to deliver some new equations. But the message is very powerful nonetheless, because it's a mechanical idea. The idea is before you break, the high tension need to transmit over long distance. If you make this really long, you can get high fatigue threshold. So Tanglemer deconcentrated stress, at least a mechanical engineering word, mechanism word, it's stress. Not only we worry about stress concentration, we worry about stress deconcentration. It's by making long chains. That has a direct evidence by now. Nobody quarrel with us. You can enhance fatigue threshold by order of magnitude. Thank you very much.
guess for some questions, I suppose. Yeah, sure, please.
Thank you for the great talk. I'm a postdoc from Dr. Sheng's group, and I have a question. I have a quick question about the synthesis of this Tanglemer-based hydrogel. So because you change the sequence of this of adding water, right? You add water in the end. So in this case you swell the polymer by water. So how to control? Then this is how to control the proportion of the water.
Or we swell to equilibrium. Yeah, this is a requirement for many applications of hydrogel. The hydrogel need to be stable in water. So the traditional way, we just do traditional way, you swell to equilibrium.
Given the proportion, you just change the concentration of the polymer.
Oh, traditional way to control amount of water, there's a traditional way. You just control it by crosslink density. That's one control, right? For a given polymer. The other control is that people design polymer site group to make it less hydrophilic. Yeah, these are two principal methods. Yeah. For us, we control the amount because we choose the chain such that entanglement density is high enough so that you're entangled. You cannot swell. Yeah.
Sorry?
Yeah.
I believe that your secret with the dough, Italians knew very long time ago. If you go to Italy and buy their bread, and then come here and buy American bread, you cut it and immediately see the difference.
Yeah.
For different dough and everything you said about entanglement.
Yeah. Yeah, I was intrigued by dough as well. So as a Chinese, I didn't know the history of dough in Italy, but dough really is serious. People have so much laws about preparing dough. I didn't study it. It could be something to do with the entangled, but it could be also have something to do with there's also chemical reactions during the preparation of dough. Sulfur reaction. So I don't know. It's interesting because I hear in the food industry, the laws about preparation of dough. Thank you. Yeah, we need to engage. Yeah, I need to engage another student.
I think we have a question to that. Yeah, you do.
Really nice talk. I just had two quick questions. One, especially now that you're studying reinforced rubber, have you done any SEM imaging to see the difference between your method and the conventional method?
So for particle ring, yes, we we have a microstride not here in the paper, right? So we do see clustering, for example. We also see the percolation. We see these things, but mostly we're interested in whether we can have a more or less homogeneous distribution. We have a lot of a particle here, just a rubber, no particle. That was a concern. Whether you have a good dispersion of particles, we do achieve good dispersion. So yeah, there are a lot of details. Part of the reason I mentioned there's a paper still not accepted. Actually, it was rejected twice by two different journals. I don't name these journals. They're terrible journals. So, but reviewers are fair. They just say, you change the process. All right. Previously, industry has a standard process how to blend particle and rubber together. Now you change the process. How can you say that your process is of value to the industry? So of course, our standard answer is this. So industry can always learn from us. If the properties are good enough, maybe they will change. So let us tell people, at least the properties are good. But the editor is such a close mind, didn't give us a chance to talk back. So we try another journal. So the message is good. The property really is good, no dispute. It's just a process itself, whether industry will adopt it.
The other quick one is just, have you seen any biological analogs of Tanglemers?
Very good question. We haven't. So it's just we haven't just we tried, but not hard enough, or just not looking at the right place. Whether entanglement plays an important role in biological tissues. Excellent questions. We raised that question to ourselves again, but answer is uncertain. My own guess is if it's this powerful, actually coming to think of it, natural rubber is highly tangled. Itself is highly tangled. It's just we human beings cut it short. Then entanglement is irrelevant to us in our products. Yeah.
Here's a question over here.
Yeah, for the Tango gel or the Tanglemer, have you explored any introduction of some chemical agents into the swelling solution to for self-healing and then further increasing the fatigue strength?
We haven't. It's a good thought. It's a good thought. Another related thought is now we already see the goodness of entanglements. So at this moment, we don't have a little hand to increase entanglement for the thread. We do a lot of entanglement here, right? There's a very dense entanglement here. So the entanglement density is almost comparable to the diameter of the thread, right? Or multiple. So we rely, in our preparation, we rely on thermal motion of entanglement. So some chemists are telling me that they are trying to use chemistry to enhance entanglements, to densify entanglements. For example, simple ideas, if you have a scaffold, right? A lot of holes in your material, then the polymer has to get through these holes, then you have high entanglements. Then after you prepare it, you can remove this scaffold. So things like that. So for chemists, it's a really good time to look at a Tanglemer. For mechanical engineer, we're already done to our extent that show entanglement has a huge impact on fatigue threshold in this case. So it's up to people with a real skill in chemistry to go further. Also to take for people who have a real application to take advantage of a newly available material. Both are very open. This story, our first paper was published 2021. Actually, I just checked. By now, there's already 1,000 citations. It's very unusual. It's a series. Yeah.
I have a question for this preparation, Entanglemer.
Yeah.
So for this preparation, I think it will be made from monomer precursor with pretty high monomer concentration, which also means that the solvent is a really small amount in the final product.
Yeah.
And so, but in our according to our cognizance, the solvent typically served as a kind of the soft agent in the final gel materials. So how can I distinguish like this improvement of mechanical strength either come from the entanglement or it comes from like the increased portion of a polymer?
Excellent question. So in our final product, it's fully swollen. So the water content is still very high. So 80, we can do 90%, for example, no problem. So water content is still very high. Right. Fully swollen gel.
I think we have maybe two more questions, then we have light refreshments out back here. So I think you have a question here.
Yes, I'm not sure if you intend to go make a product and take advantage of that, but it might be great timing that you found that the Entanglemer is better than natural rubber. Around COVID times, also there was an issue that the natural rubber tree is dying off, and airplane tires rely almost exclusively on natural rubber.
Yeah.
You have a better product. There's $100,000 a pop right there.
Yeah, we are actually approached by multiple companies, yeah, try to develop this for various applications. That's true. So, yeah.
Natural tree,
Uh,
save the tree.
yeah, it's a possibility. It's a possibility. Yeah.
I think there's a question in the back here.
So you showed by changing network structure.
Yeah.
Changed all these different properties, but you also changed the hysteresis to be drastically diminished. But of course, in many applications, the damping factor of rubber is actually something to want. So have you found any way to reintroduce that high damping factor that natural rubber has?
Say it again, I cannot hear the last sentence. What's the question?
To reduce the high damping factor that natural rubber, or to increase the damping.
High damping. No, we actually we typically we actually look hysteresis or E double prime. This we are so with Yakov's background, he come from car tire company. So we are looking for low damping. So yeah, we have a clear evidence that Tanglemer can reduce E double prime. Yeah, that is, yeah, we're pursuing that. It's a good question. So, but so I was always under the impression to have a high damping, it's relatively easy to do. Because all you need to do is have some your side group with more interaction, then you have high damping. Why is that especially challenging?
It's a trade-off between stiffness and
Okay.
damping. So if you can enhance
Yeah.
the stiffness, also increase the damping factor.
Thank you. Okay, thank you. We haven't looked at it. Thank you for that question.
I think we'll cut the questions here and thank our speaker one more time. Thank you for the.
Thank you.